All right, so when you're doing these first problems and they're asking for the electron configurations or the addresses, we need to remember that these horizontal periods, they're called, stand for the number of energy levels total in any given atom. 4, 5, 6, 4, 5, 6, 7. And these regions stand for the orbitals where the outer electrons exist. Okay, so let's give the addresses for the following. Here's aluminum. Aluminum is going to start with 1s2. It's then going to go to 2s2, 2p6, and it's going to end there on 3p1. I mean, 2p6, 3s2, and 3p1. That means the last electrons in aluminum exist in the third energy level. Cl, likewise, would be just like aluminum's, but instead of ending in 3p1, we'd end in 3p5. So this is 1s2, 2s2, 2p6. Now we got the valence shell, 3s2, and 3p5, having 7 total electrons in that outer third energy level. Barium is right here. Okay, so with barium, it's going to take a while, but it's good practice. We're going to wrap around to 56. So with barium, it would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. We're going to wrap around here to 5s, 5s2, 4d10, 5p6. Okay, that's right here, xenon, and we're going to wrap around here to 6s2, okay, giving them 2 electrons or valence electrons in the outer shell. Copper is going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, 1, 2, 3, 4, 5, 6, 7, 8, 9. 3d9. So it's weird because these are the actual electrons in the outer shell, but the presence of this d orbital really messes with copper. This is going to be a situation where when we do the name, copper is going to have to carry around a sign saying, yo, what's up? I'm Roman numeral 1, meaning I'm +1, etc. Bromine is right here. So we know it's going to end in a P5, and it's going to be a 4P5. So it's going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p5. There it is. Had to go through the 3's. So the outer orbital here, it's kind of tricky, but we don't count that. We got 2 in the s's, 5 there, giving a total of 7. So now we're going to draw the Lewis structure formation for compounds between Li and Br. So first, what we do is we draw the Lewis structure, Lewis diagram for Li. Li has 1 valence electron because it ends in S1, and Br has 7 valence electrons because it ends in S2P5, so 7. 1, 2, 3, 4, 5, 6, 7. It's got that 1 slot there. This is the low ionization energy side. This is the high ionization energy side. So it's going to pull on that electron. Remember, actually, we're going to say high electronegativity. So what's going to happen is Li here is going to lose 1 electron. It's going to be +1. Br is going to own all of these electrons. Be -1, and the formula is going to be LiBr. Let's do Ca and F. Ca we know ends in S2, so it's going to have 2 valence. And F we know ends in S2P5, so it's going to have 7 valence. So there's 1 empty slot. Low electronegativity element here that's going to want to lose electrons is going to give that. But unfortunately, we don't have enough slots, so we're going to bring in another F with a slot, and that's where that's going to go. When that happens, Ca is going to become 2+, okay? And each F in this case that now owns that octet of electrons is going to be minus. So we can put the other, I'm going to put the other one side by side just for space. And that's going to be equal to a formula of CaF2. This 2 stands for the presence of 2 of those. Here we'll do aluminum and oxygen. We know aluminum ends with S2P1, so it's got 3, 2, 3. And O ends with S2P4, so it's got 6. Slot. So we're going to donate this here, and we're going to donate this here. Now we've run out of oxygen, so let's bring in another one. 2, 3, 4, 5, 6. Slot. So we're going to donate that there. Okay. But now it looks like we're going to have to bring in another Al. Donate that there. But now we have 2 of these to give, so we're going to bring in another O. When that happens, we're going to be left with 2 ALs, which are both 3+, because each one of them lost 3 electrons, and we're going to be left with 3 O's, each having 6 electrons, and all of them being 2-, because each of them gained 2 electrons. Just kind of make it in this matrix here. And that overall formula is going to be Al, 1, 2, O, 3. Let's look at D. Carbon, we know, ends with S2P2, so it's got 4. And in this case, we're going to assume carbon's going to lose 4 electrons. We know that S ends with S2P4, so it's got 6. 2, 3, 4, 5, 6. So low electronegativity is going to go to the high electronegativity element here. But we have too many, so we're going to bring in this case, I'll put it down here this time, another S, or we'd have not enough S's. So that's going to go there. That's going to go there. Carbon then lost a total of 4 electrons, so it's going to be 4+. And the sulfurs gained a total of 2 each, so each is going to be 2-. This time I'll do them up on top. So that's going to be C1S2. Now, this one's a common one for people to do C2. If I were to give it to you like C, like this, okay, a lot of times people are going to do this, CS or C2S4. But no, we don't need that. Okay, so when we do it out this way, it really becomes evident what's going on there. So let's go ahead and just go straight to the name this time. So when we look at something like this means the charge of copper is plus and nitride is 3-. So that's going to require 3 of these to balance out that 1 nitride. We know that strontium is 2+, and we know that sulfide is 2-. They already balance each other out, so it's going to be CrS. Sodium is Na+, O is 2-. That means you need 2 NAs to balance out that oxygen there. Tin is Sn4+, O is 2-. So that means you're going to need 2 O's to balance out that +4 there, SnO2. In this case, Fe is 3+ because of that Roman numeral there. S is 2-. So you're going to need 2 Fe's and 3 S's to reach the least common multiple of 6, S3.